All right, let's dive right into this explainer. I want you to imagine shrinking down, like way, way down into a completely microscopic universe. Just picture this glowing, neon-drenched landscape where the very fabric of reality is literally vibrating with energy. Today, we are taking a seriously mind-expanding journey into the heart of a spinning crystal. And look, this isn't science fiction. This is a groundbreaking, real-world discovery from a 2026 paper in Nature Physics. We're going to explore how energy, light, and motion all dance together at the quantum level, and we're going to make this completely invisible world visible.
So start with this. When electrons lose their spin, where does it actually go? It sounds like a pretty straightforward question, right? But it's actually the hook to a massive century-old physics mystery. See, in classical mechanics, angular momentum, which is basically just the energy of something spinning, it can't just vanish into thin air. It has to be conserved. But inside solid matter, tracking exactly where that microscopic spin goes when a magnetic state changes, that has been a total black box for physicists. Until right now. We are dealing with a wild 100-year gap here. Back in 1915, Albert Einstein and Wander Johannes de Haas proved that changing the magnetization of a material actually causes the whole thing to physically rotate. Basically, this showed that the quantum spin of electrons eventually transfers to the macroscopic, rigid lattice of the material itself. But how does that transfer actually happen, step by step? For over a century, the intermediate steps, how the crystal lattice internally handles and distributes that spin, well, it remained just a postulate. We simply couldn't see it happening. That is, until the 2026 direct experimental observation that we're unpacking today. Okay, to really grasp the answer, we need to know the players. First up, the phonon. A phonon is a quantized vibration of a crystalline lattice. Now, I want you to visualize this, not just as some boring, static textbook diagram, but as a rippling, energetic, geometric wave vibrating through a dark void. When these atoms vibrate in a highly coordinated circular pattern, they create what's called a chiral or axial phonon. Basically, the crystal lattice itself is swirling and carrying angular momentum, exactly like a spinning top, just on a deeply quantum scale. So how do we actually catch these quantum spinning tops in action? Well, that brings us to our setup. The stage for this incredibly trippy quantum dance is a specific material called bismuth selenide. It's an absolutely amazing material known as a topological insulator. And because of its highly unique structural symmetry, it acts as the absolute perfect testing ground. As for our high-tech tools, we're talking intense single-cycle terahertz laser pulses with peak fields exceeding 1 million volts per centimeter. We use these extreme pulses of light to literally kickstart the vibrations inside the crystal. Let's break down this complex methodology into a super digestible 3-part sequence. It's basically like firing up a futuristic engine. Step 1, we zap the bismuth selenide crystal with a 2 terahertz circularly polarized laser pulse. Step 2, the crystal lattice absorbs that light and its spinning energy, which excites our first group of swirling phonons. Step 3, we use a secondary probe pulse to measure a completely different set of vibrations happening at 4 terahertz. Think about that. We're putting energy in at one frequency, and we're watching it emerge at exactly double the frequency. So we've got 2 main players in this quantum rave. First, let's look at the instigator, a 2 terahertz U phonon. This mode is infrared active, which means it absorbs the terahertz light directly and starts spinning. On the flip side, we have the receiver, a 4 terahertz EG phonon. Now this one is Raman active, meaning we can directly observe its trajectory using a slick optical trick called the terahertz Kerr effect. Because of the crystal's inherent symmetry, the instigator and the receiver are deeply coupled through a mechanism called lattice anharmonicity. In plain English, 2 instigator phonons crash together, pool their energy, and birth one single receiver phonon.
Okay, so the instigators transfer their energy and their linear momentum to the receiver. Perfectly. But what about the angular momentum? The spin? This is where things get really weird, and we have to prepare for an experimental result that seems to completely violate our intuitive laws of classical physics. Think about it. If you spin a gear to the right and it transfers its spin to another gear locked on the exact same axis, you would totally expect the combined energy to keep carrying that right-handed spin, right? Well, here is the massive plot twist. The 4 terahertz receiver phonon actually spins backward. Seriously. The researchers discovered that if they zap the crystal with a right-handed spinning laser pulse, the resulting 4 terahertz receiver phonon spins with a perfect left-handed trajectory. The helicity completely switches. It reverses itself entirely. Now, if this happened in the empty vacuum of space, it would absolutely violate the conservation of angular momentum. It literally shouldn't be possible. So how on earth is this actually happening?
The answer lies in a single critical number,
3. This refers to the sacred geometry of the bismuth selenide crystal itself. Specifically, it has a discrete three-fold rotational symmetry, known in the biz as C3 symmetry. Unlike the smooth, continuous, infinite 360-degree rotation that's possible in free space, this crystal lattice only looks the same if you rotate it in perfect one-third turns, or 120-degree increments. The ions exist in this rigid triangular grid, and this highly discrete environment completely rewrites the fundamental rules of how spin operates. Let me explain this with a super simple analogy. Imagine a dial that only has 3 positions. Got it? Okay, so our 2 instigator phonons each have a spin of +1. When they collide, they combine. 1 + 1 = 2, right? So the receiver phonon should have a spin of +2. But here is the kicker. On a dial with only 3 positions, moving forward 2 steps lands you in the exact same physical spot as moving backward 1 step. A spin of +2 is literally identical to a spin of -1. By spinning backward, that 4 terahertz phonon is actually perfectly conserving the crystal's overall angular momentum. In the physics world, this incredible workaround is called rotational Umklapp scattering. Okay, so we've definitively found the missing spin. But how efficient is this whole process? The researchers found that only about 3% of the absolute angular momentum from those instigator phonons is coherently upconverted into these backward-spinning receiver phonons. The remaining 97% isn't lost, though. It just kind of dissipates into the acoustic shadows. It cascades down into lower energy, far more chaotic microscopic vibrations. But you guys, that 3% coherent signal, that is the smoking gun. It is the very first direct observation of anharmonic phonon-phonon angular momentum transfer. So why does this matter? Honestly, why this changes everything is because we have finally peeked inside the black box. For a full 100 years, ever since Einstein and de Haas, we knew spin went into the lattice, but we didn't actually know the mechanical pathways. Now we do. We know for sure that the anharmonicity, the specific, slightly chaotic way the crystal lattice is structured and coupled together, mediates that transfer. We've essentially proven that the solid-state physics picture of chiral phonons carrying and conserving angular momentum is absolutely correct. I really want to anchor our conclusion with this exact quote directly from the 2026 Nature Physics paper. They wrote, "Phonon-phonon angular momentum transfer is permitted via lattice anharmonicity and conserves crystal angular momentum." I can't overstate this. This isn't just some tiny incremental update. This is a long-standing, massive hypothesis fundamentally confirmed. We finally have a direct phononic analog to the linear momentum scattering that governs literally all of solid-state physics. And the real-world applications of this, they are straight out of our cyberpunk future. By establishing what the researchers are calling axial nonlinear phononics, we now have a handle to selectively control states of matter at literally the speed of light. This means we could see ultrafast control over spins for next-generation magnetic memory and massive data storage. It means we can trigger topology switching, literally changing the fundamental conductive properties of a material in picoseconds. And it completely opens up the manipulation of chiral quasiparticles for entirely new, mind-bending types of quantum computing and electronics. Which leaves us with this final provocative thought. We've officially unlocked the secret of the spinning crystal. We actually know how to use light to make matter vibrate and transfer quantum spin completely backwards just to conserve geometric symmetry. So, how will this ultra-fast magnetic switching fuel the tech of our future? Will it lead to data processors that generate practically zero heat? Will it create morphing materials that change their electronic state completely on command? The microscopic world is glowing with crazy possibilities. Keep questioning, keep looking closely at the data, and I'll see you in the next explainer.